Hi, Honors Algebra 2 students. We're in Chapter 8, Day 9 Notes, which focuses on variation functions with non-integer exponents. In the prior lesson, we worked with variation functions with integer exponents. In this lesson, we're going to extend that to variation functions with non-integer exponents. All right, so since we've looked at similar problems before, as we go through this lesson, I'm going to encourage you as we get to each part to pause the video, try it on your own, and then start the video again and check your answers and listen to my explanations as needed. So if you don't have your calculator nearby, go get it because you're going to need it. And again, I would highly encourage you to do each part on your own before you check your answers and listen to the explanations. All right, so let's get started and read our scenario. The area of an eggshell is directly proportional to the 2/3 power of the mass of the egg. Suppose that a normal 60-gram chicken egg has a shell area of 28 square centimeters. So what we're going to do in part A is we're going to write a particular equation and then we're going to answer some follow-up questions. So just a reminder, when you write the particular equation, don't forget to define your variables first, write your ordered pair, show all of your work for coming up with your equation. Again, I would encourage you to pause the video and try that on your own and then check your answers. All right, so coming up with our particular equation, let's make sure we first define our variables. So I set M equal to the mass of the egg, and that's measured in grams, and S is equal to the shell area, which is measured in square centimeters. And keep in mind that our wording up here, the area of the egg shell is the dependent variable and the mass of the egg is the independent variable. So the dependent variable is going to be directly proportional to the 2/3 power of the independent variable. So again, mass of the egg is going to be our independent variable. The shell area is going to be our dependent variable. Obviously, you can pick whatever letters of the alphabet that you prefer. Some of you may just go with X and Y. So if you do that, X is the mass of the egg and Y would be the area of the shell. Be very descriptive with your variable definitions, including their units of measure. That will help you later as you refer back to them. So the ordered pair would be 60, 28. Again, the mass of the egg first, which is the independent variable, and the area of the shell, which is the dependent variable. All right, so if I write my variation function first, kind of generically, but with using the variables that I defined over here, it would be S is equal to K times M to the 2/3 power. So again, I'm using the 2/3 power that was mentioned in the original problem, and I'm fine-tuning it a little bit with the variables that I defined over here to the left. Keep in mind you need this K in there. It's your proportionality constant, or sometimes it's referred to as the constant of variation. So S is equal to K times M to the 2/3 power. Now if we use the specific information that we were given about the mass of the egg and the shell area, we could plug those values in, so it would be 28 equals K times 60 to the 2/3 power. Then if we solve for K, K would be equal to 28 divided by 60 to the 2/3 power. Obviously, you'll need to plug that into your calculator, so do that now, and you should find that you got this value right here. Store that in your calculator because obviously that would be the most efficient way to retain all of those decimal positions and work with that value throughout the problem. So make sure you store that in your calculator. And because of all the work that we've recently been doing with storing values in your calculator, you should already know how to do that. But if you don't, make sure you ask your teacher in class. All right, so then to come up with the particular equation, it would be S is equal to our K value of 28 divided by 60 to the 2/3 power times M to the 2/3 power. So again, I'm taking this K value and I'm just plugging it back into my equation up here that I wrote a little generically at the beginning. Now you can also in your work, write S is equal to that proportionality constant or your K value with some decimals in it. Again, I typically put the dot, dot, dot right there to just show that it continues to go on, times m to the 2/3 power. So either version of this particular equation written in your work is fine. The key thing is just to know that you need to store that K value in your calculator. Perhaps you even store it in the letter K in your calculator, but store it wherever you would like. Just make sure you use that stored value in all of your subsequent calculations. All right, part B, predict the surface area of a 1,600-gram ostrich egg. So again, I would encourage you to pause the video, try it on your own, and then check your answer. Okay, so for part B, predicting the surface area of a 1,600-gram ostrich egg, we're going to take our equation over here, either version of it. I used the version at the bottom when I wrote out my work because, as you can see, I was a little challenged for enough space to write my work in, but I used the bottom version right here. I plugged an M value of 1,600 in, and then I plugged it into my calculator. So you should get this answer right here. I'm not going to read all of it off, but you should get that the surface area is equal to that. I randomly rounded it to 3 decimals, so the surface area is approximately equal to 249.921 centimeters squared. And again, in your work, you can use either version of this equation when you're writing out your work. But when you're plugging things into your calculator, make sure you are using your stored value for K when you plug this into your calculator. And that will give you the most exact answer, even though we will round it at the end. Part C, a lizard's egg has a surface area of 0.6 centimeters squared. Find the mass. So again, I encourage you to pause the video, try it on your own, and then check your answer. All right, in part C, to find the mass of a lizard's egg whose surface area is 0.6 centimeters squared, if we go back to our equation, and again, either version of it, we're going to plug in a 0.6 for S, and then we're going to solve for M. So again, I wrote out this bottom version of the equation over here in my work because that helped me a little bit with space, but either version of this equation you can use in showing your work. Obviously, you're again going to use your stored K value. So I plugged a 0.6 in for S, and I'm going to solve for M. Now another thing that I did, and I'm okay with this, you should check with your teacher to make sure that your teacher is okay with it. But again, because this can get kind of cumbersome in writing out your work to show either this exact version or this version as I have it written right here for your K value. Sometimes I'll just let students say, okay, well, that's equal to K, so I'll just write that as K. So check with your teacher, make sure that's okay. I'm okay with that, but make sure they're okay with that. But regardless, let's go through and do the algebraic work of solving for M. We're going to need to divide both sides of the equation by our K value. So 0.6 divided by K is going to be equal to M to the 2/3 power. And then to solve for M, we're going to need to raise both sides of the equation to the 3/2 power. When we raise this side of the equation to the 3/2 power, that will give us an M to the first, because 2/3 times 3/2 will give us M to the first. And we know that what we do to one side of the equation, for instance, raising it to the 3/2 power, we need to do to the other side of the equation, raise it to the 3/2 power. Make sure you're writing this correctly and showing your algebraic work. We are raising each side of the equation to the 3/2 power, so make sure you're writing your work correctly. All right, and then we would take this and plug it into our calculator, 0.6 divided by our stored K value, all of that raised to the 3/2 power. And when you do that, you should get that M is equal to this value right here. Again, I wrote it out so that you can make sure that you got that specific value, that exact value, but I'm not going to read it off to you. Then we're going to round our final answer. Again, I randomly rounded it to 3 decimal positions, so M is approximately equal to 0.188 grams. All right, part D asks us a question that we have not encountered before. It says, does doubling the mass cause the surface area to double? And even though we have not answered a question exactly like this before in class, I would still encourage you to pause the video, think about how you might approach that, show your work, answer the question, and then start the video and take a look at how I approached it. In part D, does doubling the mass cause the surface area to double? So there are various ways in which you could approach answering this question, but we do require algebraic work to be shown. So one way you could do it is as follows, and certainly we would want you to use your equation to help you answer this question. So one way that we could approach it is as follows. Let's say we pick a value for the mass. Let's say we pick 1 gram. All right, well, if we double it, obviously that would be 2 grams. So let's plug a value of 1 in for m into our equation. Obviously, we get this surface area. I rounded it to 3 decimals as I have been doing. So the approximation for the surface area, if we have a mass of 1 gram, would be approximately 1.827 centimeters squared. And then if we double the mass value that we started with, so if I double 1, I obviously get 2. So now if I go back to my equation and I plug a value of 2n for m, and then I plug it into my calculator, again using my stored value for k, I get that the surface area is approximately equal to 2.900 centimeters squared. All right, so now if I go back and compare my results, if I look at the values for the mass, I doubled the mass value, but if I look at my surface area values that corresponded to those, this surface area, where I double the mass, this surface area is not double the surface area that I have up here. So my final conclusion is that doubling the mass does not cause the surface area to double. So again, there are various ways in which you could show algebraic work and answer the question that's being asked here in Part D. In fact, sometimes students will take the original value that was given. So in this case, in the original scenario, a mass of 60 grams was given, and they know that the shell area, the surface area of that shell was equal to 28 centimeters squared. That was given in the original problem. So they might start with that as a basis and then double that mass, which would be 120 grams, and then plug 120 grams in for mass into the original equation that we were given up here, and then figure out what the surface area of the shell would be for that particular value. So again, going from a mass of 60 to 120 is doubling the mass. Then they take the surface areas associated with each one of those and see if they are in fact double. So again, you would come to the same conclusion as we did over here, but that's another option. Bottom line is that you need to make sure that you show detailed algebraic work to support your answer, and then obviously answer the question that's being asked. All right, so hopefully you did what I asked you to do and you approached this example on your own, tried each part on your own with pausing the video and then checking your answers. Again, I think you'll find that what we were doing in this lesson is very similar to what we did in the last lesson. The thing that is different in this lesson is that we are working with variation functions that have non-integer exponents as opposed to working with integer exponents that we did in the prior lesson. So this wraps up our Chapter 8, Day 9 notes.